So we are working on biomass pyrolysis and gasification. We got 4 co-authors. Yasser Makavi is the principal investigator in this project. And Rafael Oken is from Harvard University. Soto Sanuerli is in mathematics group at Austin. So this is the outline of my talk. First part, I will introduce the granular flow and regime map. And second, give some motivation of our work, then introduce our CFD model on dry and slightly wet flow, then final conclusion. So what's the granular flow? Granular flow is a collection of large number of discrete solid particles. So it may behave elastic, solid, or fluid. So you can see this is the different granular material in our daily life. Then we look at the regime map in granular flow. So depend different flow behavior at different regime. We can divide it 3 regimes. In the faster regime, it's including the kinetic and collision interaction. Actually, we use the KTGF, it's kinetic serial granular flow. It's well developed. Then for the friction regime, we have the enduring contact. So we use the Coulomb friction law. But in intermediate regime, it's less understood because it's coexistence of friction and collision strength in dry flow. So we want to understand what's the boundary between different regimes. So this is the image just from the Tados and his co-worker, 2003. So we can see that at this boundary between the intermediate regime and the slow regime, this boundary is uncertain. And in slow regime, we use the continuous shear field to describe. And this side, the rapid granular flow, friction is ignored. So in chemical engineering, because I came from chemical engineering background, intermediate dry flow is very important in different various applications in chemical engineering, such as dense bubbling flow dead bed, particle-particle friction will leading limited bed expansion and increased bubble size and solid sludging. And the pneumatical convening is like particle wall friction leading to the pressure drop and the valve and the line blockage. How about in wet flow? So like in coal and biomass gasification, so the surface oil and tar on the particles will leading agglomeration and shear degradation and fluidization. And also in fluidized bed coating, the liquid presence leading to the undesired agglomeration and particle segregation. And also thermic fluidized reactor, we inject some liquid to control the temperature. So the liquid presence also leading to the dead zone or overheating at various the part of reactor. So for commercial CFD code, this is the most popular two-fluid model. Like for solid phase and gas phase, we got continuity and momentum equation. Also the pseudo energy equation for the balance of granular temperature. So how to handle with the shear strength? So this formula uses CFD. And also this is the solid viscosity. It came from 3 contributions, collision and kinetic and friction. So for the kinetic fast flow regime, like in CFD assumed no friction. And this the slow regime, they use the additional pros to put this formula for the friction. But how about the intermediate regime? How to describe this friction part? And also for slightly wet flow, if there's a liquid bridge between the particles, So the friction become to the fluid shear resistance. So how to describe this part of force is very important in chemical engineering. So this is our big picture. We want to answer the two questions. First is how to incorporate shear strength in intermediate dry flow and also in selective wet flow. So our strategy is first choose or develop some formula, then use user-defined function coding by ourselves. Then we put a popular commercial platform like ANSYS Fluent. So we can predict the fluid behavior such like solid concentration distribution. We also use some experimental results to validate our models. So then first we look at dry particle flow. So this is experimental device. This is called ECT. It's electrical capacitance tomography. It's a diagnostic imaging tools in medical field. So you can see that we put two sensors here, so we can instantaneously monitoring the solid concentration distribution. The blue colors means the gas and bubble here. Then the red color means very dense solid. Actually, for comparison between the experimental data and the numerical result, we just sample at least 3.8 centimeter, do some time average and spatial average. So actually, this we want to use Tado's shear stress formulas, because Tado's developed this formula like in QAT device. So this formula advantage is just combine the slow regime and the intermediate regime. So actually, this is CFD governing equation. We want to replace this part, shear stress here, and also shear stress in energy dissipation, granular temperature energy equation here. We also modify the shear stress at the boundary. Actually, this finish use user-defined function written in C code. This is the model setup, like for the boundary conditions, material, and also operation conditions. Then we look at the result. Here, we compare the three different friction models, and the triangle means the experimental result. So here we just record the instantaneous snapshot for the correction of the reactor. So in like 5, 10, 15 seconds. Then this way time average of the control plot. So you can see that for these superficial gas velocities, those three friction model got over prediction in the center, and at the near wall area, the Tado's equation behave better than to the other. This way, that's the friction kinetic theory without friction, and also Fluent default friction model use the Jackson model. Then we increase the superficial gas velocity to 0.54. So you can see the comparison between this. Tado's model also behave better near the wall. Then at very high gas velocities, because most of the area, you can see it's approaching the fast flow, even in the intermediate flow. So that's why Fluent kinetic theory without friction model behave better. We also compare the three model prediction with experimental on the bed height. So you can see that at different height, what's the solid fraction? We do the spatial average for each correct section. So we compare the bed height along with the gas velocity. So you can see that if less than 0.6, all three friction model could get relatively good agreement. If bigger than 0.6, that means we got the variation here. So how about slightly, sorry. How about slightly wide particle flow? This is ongoing work. So as we adding more liquid, so the particle interaction being through the pendular and the funicular and capillary and droplet, pseudo droplet state. So we can see that as the liquid saturation become higher, the liquid bridge between the particle will partly and fully merged and lead to the continuity fluid network. So we are interested at least pendular state. So we call it slightly wide case. So friction content will become the fluid shear resistance. Then collision content dissipate energy in both liquid bridge and particles. So we look at experimental result ECT. This is three-phase the map. You can see that because this case we keep the solid fraction constant. So this arrow just show the flow pattern transition from granular flow to slurry. So it's been through like a bubbling and bubble slitting and slugging and solid slugging. So we gave the hypothesis on the different regime, like for fast flow, it's traction content dominated by collision strength. Then intermediate flow is like liquid bridge, is viscous stress is dominate. And a very dense flow is enduring contact between the particles. But in a real system, direct solid content are very limited. So actually, intermediate regime, this interaction is very important. So we found some formula for that. First, we calculate the fluid force at a single particle level. It's function of the viscosity of liquid, diameter of particles, approach velocity, and the interparticle gap. Then we calculate it for the whole powder bed, get the normal stress. Then by analog to the Coulomb friction, we get this solid viscosity for the white case. So we add this term in our momentum equation to predict in slightly white case how it's bad behavior. So this part work is still ongoing. So this conclusion, like we already found out, developed some formula for dry and slightly white case, compare our proposals model with experimental. Also, we want to validate slightly white case. So final acknowledgement. Thanks all the people involved in this project, then the grant from Level Home Trust. Thank you.
Questions? Go ahead. You said you used turbulent flow for the model. So does it make difference between it and the laminar?
Currently, we use the K epsilon, the model. I'm not sure it's good for the list like not so time average or Reynolds average case. We will try other models like Reynolds stress model or something else.
Did you try to solve it in laminar flow or?
I think for this case, especially for high velocity case, it's not laminar flow. It's turbulence also dominate for the gas phase.
The point is that if you have like very dense flow like this, some studies suggest that there is no need or there is no effect of turbulence on the particle.
Because we are mainly interested in the biomass pyrolysis. So in that case, it's like high pressure, high temperature. So really like a interaction between the reaction and turbulence. So this case bubbling flow is just for test our model first and then apply it.
And the turbulent flow is only for the gas flow, so there is no effect on the particle flow. If there is any
actually, our mainly interest on the shear stress effect. So for the turbulence model on particle flow, I think it's very challenging. Yeah.
So I have a question,
Yeah.
and I just wonder what the appropriate measure is to be able to compare against these, the different models and the experiment. I don't know, but I imagine that some of your variables are going to be, especially when you average them over the whole of the cell, for example, they're going to be pretty insensitive to whatever model you choose. So, what's really the right measure for establishing?
Yes, I know. For the experimental and the modeling, so all the phenomena is instantaneous. So, but if for specific moment, it's difficult to compare between the ECT and the modeling. So we must do some time average or special memory. I mean, if the bubbles passing from this in center area, so it's alternatively change between the fast flow and the intermediate flow, and maybe depth flow. So that's also a very good question to let us think about how to implement this phenomena in detail or clearly. Okay.
Don't they have any questions? So just